The notes for section 6.3 give us an opportunity to look at the fundamental theorem of calculus in another way. We're going to continue our thinking about area under the curve, and now we're going to think about it as we move from left to right on a graph and how that area accumulates as you move from left to right. Also, with respect to the fundamental theorem of calculus, we could look at that formula in part 2 as a net change theorem. So we're also going to get this notion of net change theorem, where we have a starting amount, a change will occur, and then we'll have an ending amount. So let's take a look at that. First, I have included a reminder of the fundamental theorem of calculus. There are two parts to it. The first part allows us to assign a function to the definite integral, but then we think of the upper bound as a variable. So g becomes a function of x. The second part is what is often thought of as the fundamental theorem of calculus, and that is where you can evaluate a definite integral. So there are some notes that we could get from the book on this. I included a couple of notes. The function g in the fundamental theorem depends on x, which is the upper limit of the integral. If x is a fixed number, then the integral is just a definite number. It's just a definite integral and you get a number. If x were to vary, then the integral varies, and that defines a function, and we denote that with g of x. The other note is if f is a positive function, g may be interpreted as the area under the graph of f from a to x, where x is in the interval. Therefore, we can interpret g as an area so far, or an accumulation function. Note that if f is continuous on AB with positive and negative values, then the function g is actually a net area so far function. And then we have the net change theorem. The definite integral of a rate of change f prime is the net change in the original function. So this looks like the second part of the fundamental theorem. But let's rearrange these terms and you'll see where it actually looks like a net change theorem. When we set up f of b minus f of a, f of b is actually the end amount, f of a is a starting amount. So if you think about it, if you take the starting amount and add on how much is changed, then you'll get the end amount. We're going to look at some examples of this. A plane starts at 10,000 feet above sea level, and its altitude changes at a rate of f of t feet per minute. What is represented by the quantity 10,000 plus the integral from 0 to 20 of f of t dt? So time goes from 0 to 20, and our unit is minutes. So what's happening is we're finding the net change of what will happen to the altitude of the plane in the first 20 minutes. So what is represented by 10,000 plus that net change? That would be the altitude of the plane after 20 minutes have passed. So notice how there was a starting amount, 10,000, and we add on the net change. Oftentimes, students will focus on the integral and the net change and fail to remember that there was a starting quantity to begin with. If the integral from 0 to 20 were to equal negative 8,000, what does this tell you about the plane? Well, if the plane started at an altitude of 10,000 feet and the net change is negative 8,000 feet, then I would say the altitude of the plane at t equals 20 minutes would be 2,000 feet. Okay, let's work with a graphical interpretation of f prime. Let f be a function defined on the closed interval -2 to 6, with f of 0 equals 1. That gives us a starting amount, by the way. The graph of f prime, the derivative of f, consists of 3 line segments as shown. On what intervals, if any, is f decreasing? And you must justify your answer. F is going to be decreasing where the first derivative is negative. So look at the graph of the first derivative. It is negative from 3 to 6. So we're going to say f decreasing on 3 to 6 since f prime is less than 0. Notice how I report my answer about the decreasing interval in closed interval notation. Part B, find the x-coordinate of each point of inflection on the graph of f in the open interval. Justify your answer. I want to remind you about the definition of point of inflection. The point of inflection is defined as the location where the concavity changes from concave up to concave down or concave down to concave up. You could also state that it is where the second derivative of the function changes from positive to negative, or the second derivative changes from negative to positive. What you are not able to do is simply state that the point of inflection occurs where the second derivative equals 0. That is not the definition of point of inflection, so that would not be accepted on your test or your AP test. Okay, so let's look at this. We aren't actually given the second derivative, we're given the first derivative. So we're not going to talk about the second derivative. We're not going to talk about the graph of f because we don't have it in front of us and its concavity. What we can only talk about is f prime. To take f prime and connect it with f double prime would be to look at where it is increasing and decreasing. So look at f prime and determine where it changes from increasing to decreasing or from decreasing to increasing. And that will be the place that there will be a point of inflection. So notice that f prime changes from increasing to decreasing at x equals 0. And then it changes from decreasing to increasing at x equals 4. Therefore, the graph of f has points of inflection at x equals 0 and x equals 4. Part C, find an equation for the line tangent to the graph of f at the point 0, 1. This should be pretty straightforward because you should know how to find the equation of a line. You're going to need a slope and you're going to need a point. The slope formula is actually given to us in the graph. That's the graph of f prime. We're looking for the slope at x equals 0. We know that f prime of 0 is going to be given by the graph. The value of f prime of 0 is 3. That serves as our slope for this tangent line. Now we need a point. The point is actually being given to us. It is the point 0, 1. Put that information into your point slope form. Okay, in part D, we finally get an opportunity to think about our net change theorem in terms of the formula we have up above. When you are asked for values like f of -2 and f of 5, all you know is f of 0 is 1. So that's the only point you actually know about on the original function of f. Then you can use the net change theorem to help you. We want f of -2, you see. We're talking about a change that happens from -2 to 0. And we have to use 0 because that's the point we have information about. So what I'm going to do is I'm going to set up f of 0 minus f of -2, because the value at 0 would be like our ending amount, and the value at -2 would be like our starting amount, and that would equal the change from -2 to 0 of f prime of x. In this situation, we have the ending amount. We know that f of 0 is 1, so you could solve for f of -2 first, or you could just enter in the values that you know. I'm going to solve for f of -2 first. I'm going to add f of -2 to the right, and then I'm going to subtract the integral over to the left. And now I'll evaluate. F of 0 is being given to us as 1. And then the value of the integral corresponds to the area under the curve from -2 over to 0. So from -2 over to 0, I'm looking at a trapezoid. So I'm going to set up area of a trapezoid. That would be 1/2 times the height times the sum of the bases. That integral equals 4. And 1 minus 4 is -3. So I know that f of -2 is -3. To evaluate f of 5, I still have f of 0 to help me. And now I can use the actual net change theorem from up above. The net change theorem has the end amount equals the start amount plus the net change. So the end amount would be f of 5. That equals the start amount, which will be f of 0, plus the net change. And you have to know to say the lower limit and upper limit are 0 and 5. The change is happening from 0 to 5. We know f of 0 is 1, and the change from 0 to 5, again, this is going to be represented by area under the curve because that's the representation we have for f prime. From 0 to 5, we have a triangle from 0 to 3, and then another triangle from 3 to 4, and then a trapezoid from 4 to 5. So the first triangle has a base of 3 and a height of 3. The second triangle has a base of 1 and a height of 1. Also, it is below the x-axis, so I'm going to interpret it as negative area. And then area of the trapezoid is 1/2 times the height of 1 times the sum of the bases, and those bases are a 1 and a 1/2. That 2 is underneath the x-axis, so I'm going to interpret that as negative area. So we get 1 plus 9/2 minus 1/2 minus 3/4. We get 4 and 1/4. Our next example, we are given f of 6, and we are given a net change of 13 for an integral that goes from -1 to 6. Then we are to find out f of -1. Since -1 is smaller than +6, this is going to represent a starting amount. This represents an ending amount, and of course this is our net change. Our net change formula, again, is going to be f of 6 minus f of -1 equals the integral from -1 to 6. Notice how they pointed out capital F prime equals f of x. You need to make sure that's included in your justifications. Okay, we know f of 6 is 8, so that could be substituted with 8. We don't know f of -1. We do know the integral, the net change, is 13. So if I subtract 8 from both sides, and I multiply both sides by -1, I get f of -1 equals -5. Our last example, this is a question about how fast the students are arriving at school. At 7 a.m., there are 246 students at school. The rate at which they arrive is modeled by this function. So this is the rate function here. So this is the derivative already. This is the rate function. That is what you have in the integrand when you find net change. We need to find out how many students have arrived by 8:15. Now, if the starting time is 7 and our units are in minutes, then that would be 75 minutes later. So what I'm going to do is I'm going to define a function g, and the derivative of g will be n. Okay, n already is capitalized, so that's why I'm trying to point out that n is a rate function already. We don't need to take the derivative of it. It is the rate function. So I'll just use a different letter because n is already capitalized, so I'm going to use a different letter and say g. G of 75, because it'll be 75 minutes later, is our ending amount, and g of 0 is our starting amount, plus the integral from 0 to 75 of n of t dt. And we're going to use our calculator on this one. We already know that g of 0 is 246. We're going to add the net change from 0 to 75, enter that into your calculator, and you're going to put the actual function, the rate of change function, into your calculator and get a numerical answer. If you do the calculation for the integral alone, that would be 3,055 students. So in the end, you should get 3,301 students.